So in this case, we are going to consider our typical exam revision as we are preparing ourselves for the exams ahead of time. So we are given that is our March 2026 exam. So let us use that to prepare ourselves and see how we're supposed to attempt these typical questions. All right. So there we have got our instructions and information which you must read and not wasting your time. I'm just going to quickly go through these questions that we are given. Question number one, as we do understand, it is our principles of electricity. So you're given the first part, 1.1, to choose the correct term from those in brackets, and you're supposed to write only answer, right? So 1.1.1, in hysteresis, the residual flux density can be, all right, it can be increased or decreased to zero by applying a negative magnetic field strength. So to get to zero, it must be what? Reduced. So here it must be reduced. And 1.1.2, the two principal laws of electromagnetism are known as what? The two principles of electromagnetism, that is the part of what? Your Faraday's laws. All right. And on 1.13, which one, a capacitor or a resistor, comprises plates and insulating materials? So that's where it is referred as the dielectric. So that's a capacitor, right? It is the one that has got these properties. All right, then 1.4, which one of these is a force that tends to produce an electric current in a circuit? So to have electric current, it must be the electromotive. All right, to have electric, you must have electric. All right, so that's our 1.4. 1.5, any two conductors that are separated by an or an insulating or conducting materials is defined as a capacitor. Remember, a capacitor, there is a dielectric, there's a space in between. So that must be what? Insulating. All right, so that is the concept in 1.16. When capacitors are connected, all right, each capacitor has the same voltage applied to them, that is in what? In parallel. When capacitors are connected in parallel, the voltage that we have here is the same throughout. All right. So in a series, it is the charge that you consider being the same. 1.1.7, one principal sources of EMF is what? Is it the strength or the movement, all right, of the conductor and the magnetic field? It is the movement of the conductor and the what? Magnetic field. And on 1.1.8, a what temperature coefficient of resistance means higher temperature, higher the temperature, higher the resistance. That's a positive one. This one's a positive, all right? So the actual reason of doing this question paper, it is because a lot of errors. It was having a lot of errors in the calculations, also these theory. So let's revise and see. 1.1.9, which one of these is the two principal laws of electromagnetism? Something that they did ask something here, that here, two principles of electromagnet. You see, guys, they're simply asking the same thing. Two principles of electromagnetism. Here they're asking the same thing. All right. Which one is two principle of laws of electromagnetism? Again, what we had before. So that's the Faraday's laws, all right? Then on 1.1.10, which one, all right? The self-induction is the ability of a conductor to induce what across itself, to induce voltage, all right? So it must induce voltage across itself. That's self-induction. So this part was direct and straightforward. Let us see on 1.2 what we are given here. All right, we have dealt with this type of a question where we've got a generator and so on. So make sure that you do join the membership so that you can access more about these classes. So here it is a revision, guys. I'm just going to quickly consider what we are given here. So there is a generator, an EMF is given. It has internal resistance, also connected in parallel with a battery. All right, so that the two, all right, so that this combination is used to supply the load. It is used to supply the load. So we have got our generator here, which has got the internal resistance and the battery with the internal resistance as well. And these two are used to supply a load resistor. So that's our load in this case here. So that these two are used to supply. So according to the diagram, you take the currents going to the what? To the load. So that's according to the information that you are given. All right. So this is our generator, positive, negative. So that's our E for the generator. I'm just going to use 1. All right. For the generator, I'm going to use 1. Then the battery, I'm just going to use that one as 2. Then the load resistor, we're going to use L to represent that. All right. So 1, E1 for the generator, that's 150 volts, and the internal resistance of what? 0.6 ohms was given, and the battery of what? 75 volts was given, internal resistance of what? 0.4 ohms was given, and the load resistor here is our load. So the load resistance of what? 30 ohms is also given. So that is what you have. So we are supposed to apply or to use the Kirchhoff's laws to determine the current through each battery, all right, and the voltage drop across the load, all right. So here, the battery that we have, it is this battery here, guys. So that is that current I2 and this one across the load. So just going to calculate everything. So from the generator, the current is going this way since these two are supplying. So that's I1, and this one is also going out as we are given from the information. So that's going to the what? To the load. And to the load, the current across the load, which is the sum of these two according to our Kirchhoff's current law, they are going towards. So that's the sum of I1 and I2, just like that. So this is what you're going to have. And from this, you can have, that's our A, B, C, D, E to what? To F, so that we can consider the two loops where you can form equations and calculate the currents depending. With the understanding that you have, you can use the outer loop and this one and this, it's in your hands, all right? So I'm just going to use this inner loop as we have used this one before, all right? So these are the two loops that I'm going to consider, loop 1 and loop 2. So remember, from the generator, that's a positive connected to the positive of the what? Of the battery. So meaning to say, you must be very careful when you consider that loop. You can avoid, yeah, but guys, let's just use it. All right, so the first loop that we're going to use is going to be A, B, E, F. So A, B, E, F back to A. So that's the sum of EMFs must be equal to the sum of the voltage drops. That's E1 minus E2, positive to positive, you subtract. So that's E1 minus E2, the generator minus the battery. So going in this direction, we can see that from F to A, we are using this way, and that's the same direction as the current. So that's a positive. So that's current times resistance, the voltage drop. All right. Then from B to E, we are opposing the direction of the current as presented on our diagram. So that's a negative. So that's negative I2 times what? R2. Just like that. So you're going to substitute this 150 minus E2, which is what? 75, is equal to I1 times R1. R1, that's 0.6 times I1. R2 is what? 0.4 times what? I2. So this is what you're going to have. 150 minus 75, that's 75. 0.6 I1 minus 0.4 I2. So this is what you were going to have as your equation. So this equation, we are going to use it with another one. Since we've got two unknown values, we have to formulate another equation using the same concept, just like what we have just applied. So we have to consider finding another loop, all right, that we are going to work with. All right, so in this case, I'm just gonna erase this. All right, you have it, guys. Let's consider another part, which is the loop to the second loop. Our second loop is going to be from B to C to D to E and back to what? And back to the point B, where there is only one EMF, which is E. So from that, sum of EMFs is going to be E2 is equal to the sum of what the voltage drops. So that's from E to B going this way. In this branch E to B, we are moving in the same direction as the current. So that's a positive I2 times what? Times R2. Then B to C to D back to E, we are moving in the same direction as the current. So that's a positive. So that's the load current times what? Times the load resistance, where our load current is the sum of these two, I1 plus I2. So that was going to give us E2, all right, which is a 75. So here, just substitute the values that you are given. 75 is equal to 0.4 times I2. That's our R2 plus what? Our IL, which is what? I1 plus I2. So using the RL, which is 30 ohms. So that's 30 into I1 plus what? I1 plus I2. Since the first equation, it has got I1 and I2. So let us use I1 and I2 in this equation. So that was it. From here, you can expand the bracket and collect the like terms. 30 times 0, 30 times 1, that's 30 times I1 times I2, that's 30 I2. Then collect the like terms on the right-hand side of your equation. So there is I2 and another I2 here. So I1 is not affected. I1 is not affected. So that's 30 I1 plus 30 plus 0.4. That's what? 30.4 I2. So that's our second equation that we are going to deal with. 30 I1 plus 30.4 I2 is equal to 75. So that's our second equation. So that's how you play around with this. So you could have used the external loop. It is in your hands. All right. So using these two equations, I'm going to solve them simultaneously now so that we can obtain these currents I1 and I2. All right. So that is for each that you are given the generator as well as what? As well as the battery that we are having. So from here, we can see that it is in your hands. It is in your hands. I'm just going to play around with equation 1 since we are to solve for these currents I1 and I2. So from equation 1, using the substitution method, I can make I1 the subject of the formula. All right, I'm going to take this to the other side. So 0.6 I1 is equal to 75 plus 0.4 I2, like that. So to find I1, divide by 0.6, 0.6, 0.6. All right, so that's it. This is going to cancel. So I1, this is going to give us 125 plus 2 over 3. So that's actually 2 over 3, which is 0.667, or you can just write 2 over 3 I2, or as a decimal, it's up to you, 0.667. It's still one and the same. All right. So with that, that is going to be our equation 3, which we're going to substitute in what? In equation 2 to find I2. So this is what you're going to do. You are going to substitute equation 2 into what? Equation 3 into 2. That is what is representing I1, the whole part, this one. You're going to substitute in what? in I1 of equation 2, just like that. All right, so what we're going to have, it was going to be 30 times I1, where I1 is what? 125 plus 2 over 3 I2. I'm just going to use it like that. It's not a problem. All right, plus 30,4 I2 like this is equal to what? 75. So you can use a decimal. Do not worry about that. 30 times 125, you now expand these brackets. That's 3750 plus 30 times 2 over 3. That's 20 I2 plus 30,4 I2, which is equal to 75. So just collect the like terms. As we can see, I2 and I2, these two, we can add them. So that was going to be 20 plus 30, 50, comma 4, I2 is equal to, we take the 3,000 this other side, so it's going to be a negative there. So 75 minus that is going to give us a negative 3675. So divide by what? 50,4, you're done. So this is I2. So that is the current that you are going to have, negative 72,917 amperes. So we have the current across what? This is across the battery. Remember, this is our battery. The second part represents our battery. So the negative simply tells us that what we are given here is opposite. They told us that is supplying the load, but the negative is denying. So the negative is telling us that it's simply what? It is simply being charged. The battery is being charged. All right. So with I2, you can find I1 from equation what? Equation 3. Find I1. So I1 is going to be equal to 125 plus 2 over 3 times I2, where I2 is this, all right, as it is the negative 72,917. So that was going to give us I1, 76,389 amperes. So as we can see, this is from the generator, remember? So the generator is actually supplying, being a positive, it is the one that is supplying the current. Then across the load, so that we can have this one, the voltage drop across the load, you must calculate the current across the load. So meaning to say, we can utilize those currents that we have. All right, we have calculated our I1 in this case here, and we also calculated I2. Remember, this was our I2. Let's hope you're going to be able to see it properly. All right, this I2 here. So we have I1 and what? I1 and I2. So from this, we are going to have what? We are going to have IL of the what? The load, the one that is going to the load, so that we can have the voltage drop across the what? Across the load. So across the load, the voltage drop across the load was simply going to be current across the load times the resistance across the load, which we do not have this current across the load. So you have to calculate it from what? I1 plus I2. So that's it. So our I1, we have it 76,389 plus I2 with a negative 72,917 as it is. So that was going to give us what? The current across the load, all right, which is 3,475, right, amperes. So with this current, now we can determine the voltage across the load. As we can see, it is just simply multiplying 3,475 times the resistance across the load of 30. So this gives us the voltage across the load, just like that. And that was going to give us something like 104 0.25 what volts. So that's the voltage across the load. So we've got everything, the currents, generator of across the battery, and the voltage across the load. So that was it for 11 marks. Okay, so they can actually do something like this, exam guys. It's just like playing around. So just to revise, like I said, I've worked this one separately. So just go through the playlist and see from the principles of electricity. All right, 1.3, without wasting your time, you are given the resistance of a coil. All right, with this one increases from this, right? So 1.3, it increases from, so that's the resistance at a temperature of what? At a temperature of 20 is 120 ohms to this one, the second one. So this is the first one and this is the second one. So the second one, the resistance now is 165. The resistance at what? At 45 degrees is 165 ohms. All right. So calculate the temperature coefficient of resistance of this at zero. So guys, we are asked to calculate this one at zero. Given different temperatures, these temperatures, they are not, we do not have anyone that is considered at what? At zero. But the temperature coefficient of resistance is needed at what? At 0 degrees Celsius. So you use this formula. Remember the formula to use that connects these two conditions, the first condition and the second condition, which are not at zero. These two, we do not have anyone at what? At zero. All right, not at what? Zero. We do not have that. But what is needed is taken at zero. So the formula states that R1 over R2 is equal to 1 plus what? The temperature coefficient of that times the temperature 1 over 1 plus this at what? At 0, temperature 2. So resistance 1, temperature 1. Resistance 2, temperature 2, just like that. So our resistance 1 is 120. Resistance 2, that's what? Our resistance is 165. So that's equal to 1 plus temperature coefficient at 0. Then temperature 1, remember at this resistance, the temperature at what? 20. So the temperature was 20. And 1 plus this, the second one, the temperature was what? The temperature was 45. So we need to calculate this one at 0, just like that. Let us try to have this one. This is the one that we need. So what we can simply do is to cross multiply to get rid of these fractions. 120 times 1, that's 120. 120 times 45 is going to give us 5,400. 120 times 45. All right. Then you put the temperature coefficient. So, sorry, this is equal to 165 times 1. That's 165. 165 times 20. That is going to give us 3,300. All right, so this is it. So to find our unknown value, you can simply take this to the other side. So it's going to be a negative. You subtract. So this 5,300, 5,400 minus 3,300. That's 2,100. All right. 120 to the other side is going to be a negative. So you take 120 to the other side, it's going to be negative. All right, so 165 minus 120, that's 45. So divide by what? 2,100, 2,100, just like that. So that's it at 0 degrees. Our temperature coefficient of resistance was going to be 0,0214, something like that, per what? Per degree Celsius. So you take it per degree Celsius. So that's how you can play around with this type of a question when the temperatures, when the resistance that are given, I mean, they are at other temperatures, but what you need, the temperature coefficient of resistance is at what? At 0. This is the formula that can unite them at what? At 0. That's how you play around with this type of a question. All right, 1.4. We have also dealt with this condition. If you go through the playlist on capacitors, check under the principles of electricity, just around the capacitors, you see we have this 1.4 where a capacitor of 12 microfarad is charged from a 120 volt DC supply. So it is being charged, all right, previously from this condition so our capacitance 12 microfarad and the voltage at that condition is 120 volts. So after being charged now, it is being disconnected. It is immediately connected in parallel or across. So they can say in parallel or they can say connected across a discharged, that one. So when it is across, it means in what? In parallel. So immediately that capacitor was connected in what? In parallel to a discharged capacitor. This is what we are given. So it is being connected in what? In parallel. Yes, you can put this one here if you want, or you can put it like this. It is in your hands, all right? So it is being connected in what? In parallel. This capacitor that we had, which was charged previous, so it is now connected in parallel. So we have got C1 of 12 microfarad being charged. So what was its charge? The charge is from capacitance times what? Voltage. Capacitance 12 microfarad times voltage 120. So that was going to give us the charge of that capacitor 0,00144 coulombs. All right, so we have got the charge of that here because here we know that Q1 flows. So our charge is what? 0,00144 coulombs, all right? So the second capacitor, the one that is connected in parallel with, it's a what? It's a discharged, this one. It is a discharged capacitor. It's a discharged what? Capacitor. Meaning to say we do not have charge on that one. So this one, the second capacitor, which is 10 microfarad, all right? That capacitor of 10 microfarad, its charge is what? Is 0. We do not have charge. It's what? Discharged. So the condition of being charged gave us Q1, the one that we're going to use on this circuit presentation. So that is how you play around with this type of a question, all right? So from there, you can answer here to calculate the potential difference across the combination, that parallel combination. We are going to need what? The potential difference here. So the potential difference, that's simply the total voltage, all right, that you're going to need across these. So the total voltage, we know that it's a parallel combination. It is the same. VT is the same throughout. So what we can do is to calculate that, or we can calculate so many ways. You can calculate from QT. QT is the sum of what? Q1 plus Q2, all right? Where in this case, our QT is the sum of these two, all right? And we do understand that Q is the what? Q is voltage times capacitance, or capacitance times what? Voltage. So C1 VT, voltage is the same, so that's VT plus C2 VT, since this one is the same. So you can make VT the subject of the formula so many ways, guys, all right? That you can play around. C1 plus what? Here it's going to be C1 plus C2 divided by C1 plus C2. So that's it. We've got VT as the subject of the formula, which is going to be QT over C1 plus CT. So if you check the presentation that I've done from another example, I worked out in another way where you can calculate, all right, QT, because QT is simply the sum of Q1 and what? Q2. And Q1 is what? 0,00144, since QT is what? 0. So that's our QT is this in coulombs. And we know that QT is what? The total voltage and the total capacitance. So it's going to be CT times what? The total voltage. So VT, the one that we want, is going to be total charge over total capacitance, where in parallel, the total capacitance is equal to the sum of capacitors. So you add C1 and C2, 12 plus 10, which is what? 22 microfarad. So meaning to say your VT was going to be QT, this one, 0.00144 over what? The total capacitance, 22 times 10 to the exponent of -6. That was going to give us the total voltage. That's another way, so many ways. That's another way. So that was going to give us the total voltage mean, which is 65,455 volts. The same thing that you're going to obtain even from this one, because your total charge, since these are taken, you have to add them just like what we did here. So you're going to obtain this, right? The total charge is there. We already calculated it. C1 and C2, that is this one, the total capacitance, the one that we added here. So you see, this one is just combining everything. All right, so there are so many ways that you can play around with. All right, so that's it. Let's take our total charge here, 0.00144 over what? C1 plus C2, those capacitance, you just add them. 12 plus what? 12 plus 10 microfarad times 10 to the exponent of what? -6. That was going to give us the same answer that we just obtained here. So that's it. That's your total voltage, just like that. So many ways of playing around when you are dealing with what calculations, all right? So from this total voltage, now calculate 1.42, the charge across each capacitor. So you neglect now the information that you had before. To say there's a charge of this and that, this one, you take this back to default settings, all right? When now the voltage is given as what? Our total voltage is given as the one that we calculated, 65, what? As our voltage is now 65,455 volts. So you take it this way without those conditions that you had, what is going to be Q1 and what is going to be Q2. So using the voltage, because we know that in parallel voltage is the same. This is the same VT here. This is the same VT. So what we want is the charge across each capacitor Q1 and what Q2. So 1.4.2 Q1 from voltage times this, or capacitance times, it's gonna be capacitance, the voltage, that's the total voltage now, because it's the same throughout. So you simply take the capacitors, you start again like you never had these values, all right, at that given voltage. That's it. So you're going to see that you're going to have a lot of decimals that you can avoid and just having your answer maybe in microcoulombs like that. So let's say you want to write your answers in microcoulombs. All right, to have your answer in microcoulombs, you multiply by the opposite of that, times 10 to the exponent of what? Times 10 to the exponent of 6. So your answer will be automatically in what? Microcoulombs. That's it. So whatever that you get here, multiply by 10 to the exponent of 6. You get your answer in what? Microcoulombs. So that's our Q1 of 785,46 microcoulombs. So that's our Q1. So same concept to find Q2. We use the same concept, C2 times VT, since the voltage is the same throughout. So taking that capacitance value, C2, that's what, 10 microfarad, 10 times 10 to the exponent of -6. The voltage is still the same, 65,455 times what? All right, so that's it. To convert to those micro, you do like the same, multiply by 10 to the exponent of 6. This is converting to what? Microcoulombs, I mean. That's converting to microcoulombs. You simply multiply by what? 10 to the exponent of 6, whatever that you're going to get here. All right, so that was going to give you 654,550, all right, coulombs. So that's microcoulombs. So that's our Q2. It's already converted to the micro by multiplying by that 10 to the exponent of what? 6 that we had. All right, so that's how you play around. You see, guys, this just playing around. There's nothing much to consider. So that was it on question number two. So question number one. We're still on question number one, guys. All right, 30 marks. Okay, that's a lot, and it deserves that. And number two on our DC machines. All right, that was 20 marks. And let's see, 20.1, you've got all right, 2.1, a 6-pole lap wound DC generator supplies this. So it's a DC generator, all right, lap wound. So it's lap wound, all right, DC generator, all right. We want the connection of that generator. So the connection of the generator is later on described that here it is a shunt connected what? DC generator. Remember, the generator supplies current. A generator supplies what? Current. So let me just have a sketch of how this was going to look like. So we have got a generator. I'm going to have it here supplying the current on the other hand. All right. So that's here. This is our generator with the armature resistance and so on. So since it's a shunt, this is a parallel connection, all right? So that's supplying the current to the load. You can even start with this on this end. It's not a problem as long as you understand what you're doing, all right? So that is, this is part of what? Part of our load, all right? So that's it. This is our load, and this is our generator. As we do understand, the input power is going to be mechanical power here. So that's our input power, which is mechanical power. So that's it. And the output is electrical, where we're going to have the voltage, terminal voltage. And the output, like I said, is what? It's electrical. So as the generator supplies current here, the generator supplies current. So it means the current from the generator, which is the armature current, is going to supply, all right, is going to be taken into, as we consider here, another one going to the what? To the load. So the other current goes to the load, another one to this shunt resistor. Remember here, we've got our shunt resistor. So another current is taken into the what? Shunt resistor according to our understanding of a shunt connected DC generator, all right? But according to this information, there are a lot of things that were given. They're saying it's a 6-pole. So a 6-pole, the pair pairs 6/2, which is 3. So you've got pair pairs, 3 pairs, all right? The current that is at the load current is given here 60 amperes, and the voltage is what? The voltage is 250 volts, all right? Calculate the speed. So we need what? The speed. So here we're going to need the speed of the prime mover if the machine is what? Shunt connected, as we saw, and the armature is 820 conductors. So the number of armature conductors, 820. The resistance of, so the armature, from that armature, it has these armature conductors and resistance. So the resistance of the armature from our circuit here, the resistance of the armature is what? 0.2 ohms. The field has a resistance of what? Which is the shunt field here. So our shunt is 125 ohms with the flux per pole. So this is our flux, all right? Our flux per pole of 60 milliwebers, like that. So how can we determine the speed? We can see that this question is taking us to the EMF equation on calculation from the circuit, and that EMF equation that we are used to from these quantities that we are given, the general formula, where E is equal to 2, the useful flux, the speed, the pair poles, the number of armature conductors over 60 C. So the speed is there from this formula. We can see that we have got what? The speed, which we can make the subject of the formula. If you're going to cross multiply, then divide by the rest. All right, that was going to actually give us what? that was going to give us the speed. So we're going to try to do that and have our speed. So multiply this 60C times E, then you divide by 2 flux PZ. All right. So divide by that. But still, we can see that we do not have, all right, C, we have got C because we are told that it's lap wound. So C is equal to 2P for a lap. 2 by 3, which is what? 6. So we have got C. We do not have E. We have the useful flux, this one and this one. So the E now, which is the generated EMF, as you are considering what? A generator, is the one that you're going to focus from the diagram. You see now how you play around with these questions, guys. So they'll be trying to play around with you guys. That's why you've got 7 marks. All right. So to find that E, you have to consider the formula. We are dealing with a generator. So this is the generated M. So it's V plus the armature current times resistance of the armature circuit, which in this case is just that armature resistance that we are given. We do not have a lot of things to consider. So that is it. We have V, we have armature resistance. The armature current is not given. So we play around to find the armature current as we do understand your Kirchhoff's laws. So we have to find the armature current from our Kirchhoff's laws. That's the sum of what? The load current plus the one into the shunt field here. So that is what we have, but we do not have the one for the shunt. As the shunt, the voltages we do understand they are the same. So V here is the same, 250 volts. So we can find the shunt current and substitute back as the shunt current is the voltage over shunt resistance. So that's 250, the shunt resistance, 125. So you see, guys, they'll be playing around with you. So the shunt current, you have it, which is 2 amperes. So that's it here. We're going to have the armature current. The load current given 60 plus what? Plus 2. So that's the armature current, 62 amperes, which is needed here to have what? The generated EMF. So our V being 250 plus armature current, 62 times armature resistance, 0.2. That was going to give us 262.4 volts, which is our generated EMF. Then find the speed. You can see that we're done. Then find the speed with this because we have got these values. Remember here from our general formula, we have E now. So the speed can be calculated. And from this formula, this speed is going to be in what? In revs per minute. All right. So, all right. Sorry for that, guys. I do not know what's happening here. So it must be revs per minute. So that's our N 60 times C. We have everything here. C from the left, that's 6 times 262.4 over 2 times the useful flux, 60 milliwebers. So that's times 10 to the exponent of -3. All right, times the pair poles. How many pair poles? 3. Z is 800 and what? 20. So like I said, our answer is gonna be in revs per what? Revs per minute from this formula. That was going to give you 320 revs per minute, just like that. So you see, guys, how you play around with these questions. Just playing around, it's playing around the basic information. But because they know that you know this, so draw proper diagrams when answering, all right? Follow up according to the diagram, how these are given, all right? It's gonna be easier, all right? And go through the introductions, all those basics, all right? Then 2.2, we have got a short shunt compound wound. We are still on a generator, which supplies what? Current, but it's a what? Short shunt in this case. So a short shunt is going to be something like this. All right, this is a short shunt. So we're going to have the series field, which is connected in this manner to the armature. All right, so that is what you're going to have to the shunt So this is the circuit of a short shunt, if you do remember well from the notes that you have. All right, so that is our short shunt. So we have got the series field. So we're gonna need the resistance of the series field. And here from this, we're gonna have the generated EMF and the armature current going this way. Remember, it's a generator. It supplies that is it supplies the current. So the armature current going here to the series field, that's the current of the series field here. And the other current is going to branch to the what? To the shunt. This is our shunt here. So that's our R shunt. And we're going to have the current, our shunt current, which is going here. So that's it. And here is the series field. Remember that series field is the same as the one that you're going to have at the load. So that's our understanding at the load. That's the electrical from this mechanical to electrical. So you must have voltage and the output, which is electrical. All right. So across these guys, we do understand across these, we have what? The shunt. So we've got the voltage across the shunt and voltage across the series field here. So that's basically what you are going to deal with. All right, so let us get into this and try to figure out from what we are given. So they're saying here it supplies a load of 55 amps. So this is the load which is 55 amps, same as our series field, all right, same current. At the terminal voltage of 400 volts. So they made an error on the terminal volt. It is not 400. This one was going to give you a negative when you're calculating. They made an error. It was supposed to be 380 volts. So the terminal volt is what, 380. All right, what happened here? All right, here. So like I said here, they just made an error. It was supposed to be 380 volts. So the terminal voltage, 380 volts. The series field, all right, shunt, armature, all right, they are given. So we've got shunt and also that of what? Of the armature here, resistances. So the series field respectively is the first one. So our series field resistance, 0.2 ohms, followed by what? The shunt field, 230. So the resistance of the shunt 230 ohms, and the last one was of the armature here on this part. So that's where you're going to have our armature 0.18. So that's 0.18 ohms. So fill in your diagram so that you properly understand what you're dealing with. Then calculate the brush contact voltage drop if the magnitude of the generated EMF is 410 volts. So the magnitude of the generated EMF is what? 410 volts. Calculate the drop of what? The brush, the voltage drop, which is the brush contact. All right. So remember the EMF, as you are to consider our generated EMF, we are dealing with a battery. So where you add, all right. So it's going to be the terminal voltage, then you add the armature current times the resistance of the armature circuit. All right. So where you consider the resistance of this one, armature current times the resistance of the armature circuit, where the armature current flows, that is where you're going to have the armature current times resistance of armature. And you're also going to consider R brush as part of what? As part of the armature circuit. So the brush, you can consider it as a voltage drop. So consider this separately now, armature resistance separately. Then you consider V brush and what? There is also the series, because the armature current is going to also branch here and the other one to the series. You consider the one for the series, not the shunt here, but the series, all right, to give us the voltage drop of the series. So it's actually what I'm trying to say, the V shunt, you separate it, all right? So you take the V series and this one, the drop here for the armature current and armature resistance. So this is the formula that you're going to end up with. All right, so which is simply ISE for the series times resistance of the series field. So that's it. We can make that one, the brush, the subject of the formula. So therefore, V brush was going to be equal to E. You take all these to the other side of the equation. So they're going to be negative V, negative IA times RA minus what? The series field, the series here. All right, so that's it. We are given the generated EMF, V, we have got this. The armature resistance we do not have the armature current. The series field resistance, remember, we have, and also the series field current as it is equal to the load current. So this one and this one we have. So as we can see on our question, it is just to calculate what? The armature current. That's the unknown value. So using your diagram, you have to figure out how to find that armature current. All right, so our armature current, as you can see, it is the sum of these, the series field and the shunt as it is from the supply. So it is the sum of the series plus the shunt, where the series is given as it is equal to the load, but the shunt is not given. We do not have that. The shunt was going to be calculated if we have V shunt and R shunt. So you're going to calculate I shunt from there. If we have V shunt and what? R shunt. So we have R shunt, but V shunt we do not have. So you see, guys, we are so much limited. So where can we calculate V shunt? V shunt and the series, those are the ones adding up to the V that you're given. So to find V shunt, we use the V, which is equal to the series plus what? V shunt. So we can say V minus V series is equal to V shunt. So that's it. The V, we have it. That is the terminal that we are given of 380. All right, minus the series. Now this one, that's that's current times resistance, remember. So it's series, that's current and its resistance of the series. All right, so the current is that one, 55, which is the same as the load current. And the series resistance is what? 0.2. All right, 0.2 here, sorry for that. So that's 0.2. So this is going to give us what? The shunt voltage. So our V shunt from this calculation, like I said, they made a mistake of using 380 there. So it was going to give us 369 volts. That's our V shunt, which we need here to find what? I shunt. So V shunt, you substitute here as it is 369 over R shunt 230. So that was going to give us I shunt of 1,604 amperes. So with this I shunt this one, you then take it there to find what? The armature current. So therefore our armature current from the series, remember the series, that's our load current, they are flowing on the same path. 55 plus what? The shunt current, this one, 1,604. So that's how you play around with these questions, guys. As we can see, just playing around like that. So with this, you can calculate or determine what? The voltage, I mean the current of the armature here, sorry. So the armature current, 55 plus 1, that's 56,604 amperes. So with this armature current, we know that it was the one that was limiting this calculation here. So you have to drop it into the calculation to find V brush. As we are given our E as 410, subtract the voltage, which I say they made a mistake. It was supposed to be what? 380. All right, the armature current and armature resistance. Remember, we have calculated our armature current. So it is just substituting all right, 56, sorry. That's 56,604 times what? The resistance of the armatures, which is 0,18, minus the current of the series field, our load current, 55. So that's 55 times its resistance of the series. And the series, our resistance is what? 0,2. So that's how you can play around with this type of equation. So you have got V brush in this case. So this is our brush. The voltage drop across the brush, 8,811 volts. So that was another error which we had on our formula sheet. I mean, on our memo, guys. There were a lot of errors, like I said. But that is how you play around this type of equation. All right, so we got our V brush. All right, that's little bit calculations. As you can see, 8 marks. 8 marks is not for granted, guys. All right, so let us consider another part and see which is our 2.3. Again, 5 marks. What is it exactly that we are having for the 5 marks? Let's see. All right, so there we are given that's 2.3. Calculate the total resistance of the starter. So we are dealing with the resistance of the starter in this case, all right? From what we given here, we have to consider some of the other things that are to be considered, right? 2.3, total resistance of the starter, it's a 410 DC shunt motor. So remember, a motor, it takes in what? It takes in current. So it was supposed to be like this, a shunt field. So I just want us to see some of the things that affecting our question this time. All right, so there's a motor. It takes in current. So from the load, the current is entering to this side. So that's it here, our armature current, this and that, our E, and so on and so on. Okay, the output now is mechanical, the input being what? Electrical, and so on, the voltage, and the input is the one that we are given, 410 volts. So the input power is also given 15 kilowatts. All right. Then the maximum armature current is not to exceed. All right. Take note there. The maximum what? Armature current is not to exceed 1,6 times full load armature current. So which one is this? This is the starting current, the maximum one. So the starting current is not to exceed 1,6 times of what? Of the armature current, which we do not have the armature current from our circuit here. So we are limited, right? So at full load, that is what we are given. And this, the armature resistance, given that our armature resistance is what? 0,32 what? 0,32 ohms. Neglect the current flowing through the field. So neglect the current flowing through the field. So you take the field into neglect, like there is no current that is flowing through the field. So if it is like that, it follows that the load current will be equal to the armature current. So you see, guys, how you do answer the question. In this question, they said neglect that current that is flowing through the field circuit here. So the shunt is not taken into consideration. So it means the armature current will be equal to what? The armature current will be equal to the load current, where the load current can be calculated from what? Power, as we've got power, it's voltage times what? Times the load voltage times what? Voltage times the load current. So it means that's simply the input power over the voltage to have the armature current at full load. That's how you're gonna work with what? The current that you have at full load. That's it. It will be equal to that. So the input power, 15 kilowatts, that's 15 times 10 to the exponent of 3. The voltage is what? 410. So our armature current is going to be 36,585 amperes, which is needed here to calculate what? our starting current. So our starting current I start is gonna be 1,6 of what? Of this one, 36,585. So that was gonna give us a start of 58,536 amperes. So the question is not about the starting current, but the question is about what? The total resistance of the starter. So it is to calculate our R start. So how are we going to have our R start in this case? So what we are going to consider in our case is that remember, this circuit is neglected. So our starting resistance is going to be taken from the total resistance when we have our voltage and what? And the starting current. So our R start, all right, our R start for us to have this one is going to actually change, all right? So it's actually going to change a lot of things from our formulas, the way that we are used to. So it's going to be like this because we neglected that. So it's going to be the total resistance RT minus the resistance of the armature circuit. So RT is the one from the starting current at the given voltage. That's the voltage that is affecting us now. So let's find RT from there. So that's how you start. That's how you play around when it is adjusted like this. So your voltage, terminal voltage, you have 410. So guys, electrotechnics is just formulas. You see, guys, if you just understand the basics, then you use those formulas, you're done. So that was gonna give us 7,004 ohms with that armature resistance of 0,32. You can calculate this one because you simply have to subtract these two. 0,32 of the armature, that's giving us 6,684 ohms. So that's it. We've got our starting resistance. Our R start at the end of the day is determined from this information. So you see, guys, it's just a matter of playing around the information. So that was our question number 2, 20 marks, right? Then number 3, AC theory. AC theory, all right, 3.1. Calculate the power, all right, in kilowatts when the load is connected to, there's a voltage frequency, right? Voltage frequency and also a power factor, right? So you can calculate the power since this is single phase. So that's true power that you're calculating. So voltage times current times what? The power factor, that's direct as it is. So 240, our current, 15 amperes times the power factor 0, what? 0,8, like that. So that's 2,880 watts. They said in kilowatts, follow the instruction, divide by 1,000 to convert to what? To kilowatts. So that was going to give us 2,880 kilowatts. All right, so that's our true power. This is true power that you're calculating. Then on the other part here, we're supposed to just separate these. Let's just hope, guys, you will understand what I'm just gonna do here. I just need to separate this part. I see as if it is for me to have like the information. So this is 3.2, guys, all right? 3.2. Sorry for that. This is our 3.2. I'm just gonna separate. What have I done? I want to put it here. All right, on this part. All right, so this is our 3.2. Just for me to properly take this information, let me just do it here. So 3.2, the armature of an alternator rotates at this speed. So that's the speed is given of 3,600 revs per minute. Why are we given the speed? So that we can calculate the angular speed from there. Omega is 2 pi n over 60. 2 pi times 3,600 over 60 in rad per second. So that's 120 pi rad per what? Rad per second. Okay. So between the poles of a magnet, calculate the following, all right? If the maximum voltage of the generated wave, so this is the maximum one that you're given. So E max is given as what? 36 volts, all right? And this is a sinusoidal that you're given, all right? So meaning to say, if it is a sinusoidal, it simply means E, that is the instantaneous value, E is equal to E max like this, all right? The sine omega t, so it's going to be sine omega t. So to convert to degrees, you multiply by 57.3 degrees, all right? So that's basically a sine wave from a sinusoidal that you're given. 3.2.1, the frequency. Calculate the frequency, all right? Frequency can be calculated since omega is there, the angular velocity that you are given. We can calculate frequency from there as omega is equal to 2 pi f. So divide by 2 pi by 2 pi, you have your what? Your frequency. So frequency is omega over 2 pi, just like that. Our omega, 120 pi over 2 pi, like that. 120 divided by 2, that's what? That's 60. So this is our frequency, 60 hertz. All right, so we have a frequency of 60 hertz in this case. Okay, let us move on to the other part of the question, which is to determine 3.2.2, the instantaneous EMF after this time. All right, instantaneous value, as we have got our instantaneous what equation, as we are given a sine wave. So that's our E is equal to E max. All right, so we're just gonna substitute what we are given, all right, in degrees. All right, so then let's just calculate this because we've got the time. So let's just substitute direct from the formula. E max, that's 36 times the sine omega. We have that omega here, or omega is what? 120. So 120 pi times the time, which is this one that we are given, our time being what? 0.006 times 57.3. So the 57.3 degrees is for you to use your calculator in degrees. So you use your calculator in what? In degree mode as it is. You do not change it to the radians, this and that, all right? So you press your calculator as it is. There no effect. That value that you're going to get is your value of E, which is 27.735 volts, all right? So that is what you're going to have, all right, which was what you're going to have at the end. Okay, so that was it on 3.2. Use your calculator in degrees as it is. Then the maximum time from the instant 0 to reach this voltage. So our instantaneous voltage, instantaneous EMF this time is given 24 volts. All right. For the first time, all right, we have to calculate the time taken. So what is the time taken? Remember, Emax is given. Our Emax is this one. So you're going to simply substitute back into that formula again as it is here in degrees. So our E is the one that we have, the instantaneous value. So 24 is equal to our Emax is what? 36. 36, the sine of omega t, or omega is 120. So that's 120 pi, 120 pi times the time. Remember, you need to calculate what the time. So you do not know this one, the time, but in degrees, we're going to use what? 57.3 in degrees for us to have our answers properly without changing the calculator mode in exam, so that you do not confuse at the end of the day. All right, so we need to find the value of t. That is the question here. It is to solve for what? For t. How can I solve for t? I can simply divide by what? 36 here by 36. So this cancels out. So simply the sine of 120 pi t times 57.3 degrees is going to be equal to 24 over 36. So I need to get rid of the sign. To get rid of this sign, I'm going to write this side as what? Arc sine, arc sine. So this is what arc sine here, arc sine of this. So on your calculator, shift sign, you press that arc sine of that. So it was going to give us 120 pi t times what? 57,3. Remember, in degrees, your calculator, because this is in degrees, so use your calculator as it is in degrees. Don't change the mode, all right? When it is like this, in what? In the degree mode, you are going to obtain this in what? In degrees. Arc sine, you obtain the angle. From arc sine, what you're obtaining is what? Is the angle. So it was going to be 810. So divide by 120 pi to obtain t. Divide by 120 pi times what? 57,3 degrees. 120 pi times what? 57,3 degrees. So this was going to cancel. This cancels. You remain with what? T. So simply divide this. All right. So that was going to give you the time of something like you're gonna get 0.00193555 like that in a seconds. So you can convert it to milliseconds. Simply multiply by the opposite, 10 to the exponent of 3 to convert this, to write this in milliseconds actually. So that was going to be 1 comma something there, 1,936 milliseconds. All right, that's converting to what? To milliseconds. So you can have your answer in milliseconds like that, all right, which is easier to present. Or anyway, guys, that you do understand, and it's still okay like that. All right, so you can see it's just playing around with given information. So that's 3.2.3. All right, then let us move on to another part. Okay, 3 point. I see that there is another part. This is 3 point. I left 3.3. All right, there, here. All right, 3.3. Remember, I separated. All right, I remember. This is our 3.3 here. On 3.3, we are given a coil with the resistance of 25 ohms and inductance. So this whole part is representing a coil. So that's 3.3. So there is a coil, it has resistance and what? And inductance. Then later on is connected in series with a capacitor as we are given here. So this whole part here is representing what? Is representing our coil. All right, so this whole combination is connected to an alternating voltage, and this is like that. All right, so here the resistance 25 ohms, and the inductance, our L is what? 52 millihenries. The capacitance here is what? 320 microfarad is connected to this 220 50 hertz. So the voltage 220 volts, frequency 50 hertz, like that. So that was simply the circuit, and in series, you know that the current is going to flow out throughout, which is the same. All right, so from here, calculate the following: the inductive, all right, 3.3.1, the inductive and capacitive reactance of the circuit. So that's XC, inductive XL. So 3.31 XL can be calculated 2 pi FL, remember? So 2 pi times the frequency, 50, inductance, 52, millihenries times 10 to the exponent of minus 3. So that's our XL was going to be determined when there. There's another question also that I saw the memo was having an error here. All right, anyways, let's see. That's your XL, then XC of the capacitor 1 over what? 2 pi FC. All right, so you know your formulas, but you've got this in your formula sheet. So 1 over 2 pi times the frequency, which was 50, the capacitance value, 320 micro times 10 to the exponent of what? -6. So that's the reactance of the capacitor, which is 9,947 ohms. All right, so you needed actually these values, your XL and your what? Your XC. All right, so let us just have this one here. So our XC 9,947 ohms, our XL 16,336 ohms, like that. Okay, so this is what you had, and 3.3.2, the voltage drop across the coil, this one, the coil. So remember, the coil is the one that has the resistor and what? The inductor. There is a resistor and inductor on the coil. So to find that, there are so many ways, all right? We can say the voltage across the coil, since the current is the same, we're gonna need what? The impedance of the coil here. So it is simply the total current times the impedance of what? The coil. Where the impedance of the coil, we can calculate. We do not have the total current, so you're limited. To calculate the total current, let's say we need the total voltage and the total impedance here. So the total impedance we do not have. All right. So it was just going to be steps like that, guys, electrotechniques like that. So you have to find what you're not given, ZT. So the total impedance is what? Since there are three of them in a circuit, the total impedance comprise everything. So just compare between XL and XC. You can see XL is greater than XC. So it's best for you to subtract XL minus XC. To write XC minus XL is not a problem because the formula here you're going to square at the end of the day. Here, this is R squared plus the difference XL minus XC squared. Even if you're going to say XC minus XL, it was not going to affect because at the end you're going to square your values. But it's just best for you to write starting with the bigger one, the bigger minus the smaller one. So that's the total impedance, remember? So our R squared resistance, that's 25 squared. Then subtract here XL, 16,336. We are subtracting what? XC, which is 9,947 squared under the square root. That was going to give us the total what? Total impedance, our ZT of 25,803 ohms. So we're talking about what here? Total impedance, right? So we have the total impedance. The total current can be determined from the total voltage. So that's the total current can be determined as the total voltage is 220, the total impedance of 25,803, the total current was going to be from this calculation, guys. What is it that I obtained? I obtained something like 8,526 amperes. So that's our total current. Why are we calculating the total current? We need it here. And the impedance of the coil we do not have. We calculated the total impedance, not of the coil. The coil, it comprises of the resistor and the inductor. Guys, be very careful about that. So here you must be very careful. Let me erase this, our total impedance, as we now have it. So here you need that of the coil. So let's calculate the impedance of what? The coil. The coil, that's the resistor and what? The inductor combined together. So Z coil from the resistor and the inductor simply gonna be what? R squared plus what? XL squared under the square root, as we have got as we have got our Z as the sum resistance, and this is our X. So it's R squared plus X, where our X is what? XL. So that's the formula for Z. So Z coil is going to be the square root of R, 25 squared plus XL. Our XL, remember, we calculated that 16,336 squared. Only for the what? For the coil. What is affecting the coil? What is affecting the coil? This is to the exponent of 2, guys. 25 squared, 16,336 squared, all right? So that was going to give us the impedance of the coil of 29,864 ohms. So they were dealing with the coil only. So therefore, its voltage can be what? Can be determined. So our V coil is going to be the total current, because in the series current is the same. So total current 8,526 times what? The total impedance. I mean, then times the impedance of the coil, 29,864. So that's going to give us the voltage drop across the coil, just like that. So that was going to be 254,620 volts. All right. So that's it. That's how you play around with these typical questions, guys. You see, just a lot, but not that much. All right, 3.3.3, the voltage drop across the capacitor. So across the capacitor, we're just going to need the total current and the reactance of what? The reactance of the capacitor. So that's it on 3.3.3. So from the total what? From the total current that you calculated, that's going to give us the voltage across the capacitor as the current is the same. Then you use the reactance of what? The capacitor. So our total current, we have it 8,2, this that we're given. So we'll just multiply 8,526, 8,526. What are we multiplying to? To the reactance of what? Of the capacitor. 9,947. All right, so that was going to give us the voltage across the capacitor of 84. All right, so this was going to be 84,808 volts. All right, so this is the one that you are going to simply take as you are referring to the what? To the capacitor. All right, so you see, guys, how you play around, just a matter of playing around. Right, let's move on to the transformers on question number 4. 4.1, the magnetizing component, and this, so we have got that idea where there is magnetizing, and we're going to have so this is our magnetizing, all right, the no load, and this is our core loss given at a certain angle in between at no load. So the magnetizing is given here. This was just 3 comma, it was an error, this one. So the magnetizing, it is 3,22 amperes. And the other one, the core loss is this one, 1,2. So the core loss is 1,2 amperes. So 4.1.1 was the no load current, this one, which we can take from our Pythagoras theorem. All right, so the no load current is simply the square root of what? Magnetizing squared plus core loss component. That's it. So here the magnetizing is given, which is 3 comma what? 3,22 squared IC 1,2 squared. So that was going to give us 3,436 amperes as our no load current, and the no load power factor 4.1.2. The no load power factor in this case, that's cos. All right, remember this, I see it is equal to IO cos what? Cos theta. So you can take from IC here, just divide by what? Just divide by IO here, divide by IO. So it's going to be IC over what? IO. So that's IC over IO, where we've got our IC 1,2. Our IO is there. This is 3,436. Okay, so you just divide and you've got your no load power factor, which was going to be 0,349. Okay, so that's what you're going to have. Then 4.1.3, what we need now is the open, right? The power on open circuit, if the transformer, we have got the voltage, so that's our V1. So yes, we can calculate the power on open circuit. That is the power on open circuit. There are two ways. From that, we can use the voltage, and we use what? The core loss times IC. So that's another formula that you can use, or you can use this formula from the no load current. It's going to be V1 no load current times what? The power factor at what? At no load, the no load power factor. So that's another way right? So using this formula, it was just direct. That's V3, this one, 1,100 that you're given, times IC. Your IC is given, sorry for that. Our IC is what? 1,2. Remember that you're given this. So that was going to give us the power at no load of 1320 watts. Okay. From this one, it was just gonna be a little bit different because you are using rounded off values. So V1, that's the only value that is not rounded here, 1,100. The no load, you calculated this, it was a rounded off value. So you're using something that was rounded off. The power factor, this one was also rounded. So we are using rounded off values. So definitely it's going to affect our answer 1319, comma 08 watts. So that's another formula that you could have also used, even though it's just a little bit slight difference, just a slight difference that you're gonna see at the end from these two calculations. All right. Then another part on our transformers, it was here 4.2, where we've got a no load current. All right. A no load current is given 20 amperes. All right. Again, a no load current is given 20 amperes to this combination V1, V2, or E1 and E2. All right, the power factor, for that power factor, for that no load current, the power factor at no load is given as 0,4. Right, the primary winding has got 120 turns, 140 N1 on the primary, 140 turns, and the supply frequency, the frequency is given as 50 hertz. Calculate the following 4.2.1, the maximum value of flux in the core. So 4.2.1, the maximum value of flux. We can have it since we've got this E1, E2 from the generated EMF equation. Since we've got N1, so N1 goes with what? E1. So from that EMF equation, E1 is equal to 4,44 times frequency, the maximum flux times our N1, which is the number of turns. Yes, the maximum flux is here, so you can simply divide to obtain the maximum flux. So it's going to be E1 over what? 4,44 times frequency times N1. So we have got everything. Okay, yes, we've got everything. Our E1, that's 3,000. So this is 3,000 over what? 4,4 for 4 times the frequency 50 hertz. All right. And a number of turns N1, 140. So that's it. So our maximum useful flux here was gonna be, that's the maximum flux, what's gonna be 0,09. All right, so it's gonna be 0,096 52509, something like that, in Webers, all right? So you convert to milliwebers if you want, just multiply by 10 with exponent of 3. Your answer will be automatically in milliwebers, 96,525, all right? In what? In milliwebers. You can convert it by multiplying by 10 to the exponent of 3, whatever that you're having on your calculator. Then the power loss on no load. So on no load, we have the voltage, remember V1, and the no load current, the power factor at no load, everything is given. So this was direct power at no load. You're just going to use V1, no load current, and the power factor at what? No load. So V1, 3,000, all right, times the no load current, 20 amperes. The no load power factor 0,4 as we are given it. So that's it. 3,000 times 20 times 0,4 is going to give us 2,400. 2,400 watts, or 24,000 actually. 24,000 watts, which is approximately, not approximately, but 24 kilowatts divided by 1,000. So that's 24 watt. kilowatts. So that's it. Then the value of what? The magnetizing current. As we have got the no load current, remember from here, these two, they've got relationship, magnetizing and the no load. The magnetizing is no load, sine of what? Sine of that angle. All right, remember this relationship, which you are also given. So that's something not to worry about. All right, so you can calculate that from the no load current. All right, so 4.2.3. So our magnetizing current is no load sine of what? The angle, theta, the angle there at what? At zero. That we do not know. So you can calculate it from the cos. So the angle from cos, since cos is equal to this, so therefore our angle is equal to what? Arc cos of 0.4 in degrees. Use your calculator in what? Degrees. So our angle was going to be 66.422 degrees. So that's the angle that we are going to use here to find what? Our magnetizing component. So since we have got our no load of 20, multiply to the sine of that angle, 66.422 degrees. So that's going to give us our IM value, 18,330. Right, this was going to be a zero, so do not worry about that. 18,33 amperes. So that's how you simply play around with these typical questions. As you can see, guys, it will be like that exam. They want you to play around with the information that you are given. So if you are to consider this one, five on question number five, that's our AC machines, all right, 5.1. That's the voltage frequency of a three-phase induction motor. The synchronous speed is given, so that's our synchronous speed, 5.11. Calculate the following. That's the rotor speed, all right? If the induction motor is operating at a slip of what? 30%. So the slip is 30% as a decimal, 0.3. So we can calculate the speed of the induction motor, which is N, or you can write NR, the rotor speed. So that's from our slip, which is NS for the synchronous minus NR over NS. All right, as a decimal, if you are using this decimal. So just use as a decimal, 0.3 is equal to NS. You are given in revs per minute, 1,300 minus NR over 1,300, all right, over 1. So cross multiply 0.3 times 1,300. That's 390, all right, which is equal to 390, which is equal to 1 times 3,000 or 1,300 minus NR. So take this, it's going to be positive, and this one here is going to be negative. All right, minus 390. So that's it. You've got your NR, the speed of 910 revs per watt per minute, just like that. And the number of poles, if the induction of the induction motor, the number of what poles. So the number of poles we can calculate from our synchronous speed, because the synchronous speed is the one that has got the number of poles. Synchronous speed is equal to 60F over pair poles. So you can find the pair poles. P is equal to 60F over what? NS. You divide by NS, 60 times the frequency, 50 times the synchronous speed of what? 1,300, just like that. So this gives us the pair poles, which was approximately 2.3 something. So this approximates to what? 2 pairs. So we have got 2 pairs. So therefore, how many number of poles from 2 pairs? Each pair has got 2 poles. So number of poles, or number of poles will be simply be equal to 2 times what? 2, which is 4 what? 4 poles. We are now answering the number of poles direct, okay? Then draw a full label diagram of a capacitor start, capacitor run, single phase induction motor. So a capacitor start, capacitor run is given this manner from our supply, all right, to the main winding, auxiliary, the rotor, then the centrifugal, then we've got the start and the run capacitors in parallel like that. So that's basically what you're going to need. All right, let's move on to question number 6. Generation and supply of AC power and also measuring instruments are there. So 6.1, artisans, technicians, engineers work tirelessly to keep power stations up and running. Refer to figure for coal-powered station below and answer the following questions. Name 5 stages represented by letters A to E. So which stage where there's a storage dam? This is A. That's our coal storage. This one, that's our coal storage, or a coal bunker, a bunker. This one, or that's the coal supply. All right. Then B is part of the boiler. This one, where there's water. So this is our boiler or the steam generator. Then C, as we have the condenser, then here the generator. Here, I don't know like what actually happened, but this is supposed to be your steam. Since the generator is labeled the other one, so we're gonna take our steam, then the other one will be the steam turbine. This is a turbine, the whole part. So we take that one as our steam turbine, since the generator is separated. Then here, since the transformer, this one is gonna be the transmission line. So let's take this one as our transmission what? Transmission lines. Okay, so that's it. And 6.2, given that we have got the value of a resistor, this one is measured by a what? Volt ammeter method. So remember, on a volt ammeter method, there is a short shunt method and a long shunt method. So let's see the connection. Here, the voltmeter is connected directly across the resistor to be measured, directly across the resistor to be measured. So that's a short shunt where the ammeter is on its own like this. Then this is directly the voltmeter here is connected directly to the what? To the resistor to be measured, which is our Rx here, the resistor to be measured. So that's going to be a short shunt. Okay, so that is, we are given the ammeter reads. So the reading here of the ammeter, all right. So the ammeter reading is what? 2.5 amperes. And the voltmeter here across the voltmeter, 120 volts. Then the resistance, the internal resistance of that voltmeter, this our RV, internal resistance, 700 ohms. Then, okay, so that's it. 6.2.1, what will be the unknown resistance approximately? So our approximate value is the one that we need. Our approximate is going to be simply the voltage over current. All right, you ignore everything. So you take voltage and the current across the ammeter, voltage over ammeter current. So 120 divided to the ammeter current of 2.5, that's going to give us 48, all right, 48 ohms. Okay, then accurately, all right, so this is 48 ohms. Then accurately, that's where we can involve our calculations. We need to find Rx properly. All right, so remember this current is going to be IV and this is going to be IX here. So what we can do is to play around with our diagram. Rx is going to be taken from this voltage, since it's the voltage across, so it's V over Ix. Voltage is the same across in parallel. So that's voltage over Ix. But we do not have Ix. So Ix can be taken from our Kirchhoff's current law, the one from the current is flowing towards. So IA is the sum of IV plus IX. So want IX, take it to the other side. So that's equal to, that's equal to IA of the ammeter minus IV. which we have this one, but we do not have IV. So IV, we can calculate there is resistance and voltage here. So IV can be what? Can be determined as we have voltage and what? Resistance. Voltage 120, resistance 700. So you see, guys, this one is just playing around now, playing around 0.171 amperes. So that's it. We take it here to find our IX, the current across the unknown resistor. So the current across the unknown resistor is going to be IA of the ammeter 2.5. We subtract the 0.171 that we calculated. So that's IX, the unknown current across that resistor is 2.329 amperes. Then we're going to take it here to find what the voltage, to find the resistance of the unknown resistor accurately. All right, so the voltage across is the same, remember, 120 over 2.329. So this was going to give us the resistance from the unknown current that we calculated. So that's it. 51,524. 51,524 ohms. Okay, so that was what you're going to simply obtain from these calculations. And another one, it was to determine the percentage error. All right, 6.2.3, the percentage error in the value of the resistor, 6.2.3. So percentage error can be taken from the actual, this one, so the accurately. So you take accurately minus the approximate value, all right, over the accurate times 100%, since it is a percentage multiplied to 100%. So Rx, we have it 51,524. The approximate is what? 48 divided by what? 51,524 times what? 100%. So that was going to give us the percentage error of 6.840, which is 6.84%. So that's how you simply attempt these typical questions to obtain 100. Just go through the questions as we have our syllabus, introductions, and so on. So just go through all the basics and revise everything in the light as you are revising, preparing yourselves for the exams ahead of time. Let us communicate where we do not understand the comment section, and also utilizing our community section, we can communicate better using this platform, all right? So that where you do not understand, we can have a recap or look into that, and also join membership for more lessons for your N4, for more lessons. Once you join, it opens up all lessons under N4 that are that we are having on our membership platform. So that is it, guys, till we meet again.